Start. So welcome back. So the aim today, and it's not going to be a too in-depth presentation, because we will try to mix in some summary as well and put things into a context so that you see the things we have gone through during the semester. But the idea is to give a short introduction to generative adversarial networks. Sometimes I don't know why, instead of generative, I say generalized. So I just mix up the words, but it's generative adversarial networks, which is a very popular method, and it's been extremely popular, especially in imaging. And it belongs to the class of so-called generative methods, obviously. It can deal both with supervised, unsupervised, and a mix of supervised and unsupervised data. I also wanted to say a little bit more about the diffusion models and the codes which we had from last week, which we did not get time to discuss properly. I have a series of summary slides, and if I get time, I will make a short video of that one, because that will be for next week. But next week, the plan is that we just spend the time discussing the projects. So next week, instead of having a lecture, we will most likely just use the time from now till roughly 4 o'clock to work and discuss the projects. And you probably have many questions, etc., etc. So the idea then is simply to use that time for that. So no lecture next week. So the last topic of the semester is then going to be generative adversarial networks. I will jump a little bit between the slides from last week and this one, because I also wanted to say something about the codes for the diffusion models. But before we do that, I wanted to, in a way, sneak in a kind of summary about the generative methods. So there are some reading recommendations, and the codes which you will find here are actually codes for the GANs, which are taken from Rashka's textbook. And many of you have been using that one in connection with the FYS SDK 4155. And in the chapter 17, there is actually a pretty detailed description of those codes. There's also another textbook by Babcock and Bali, which is a very good one, which then uses TensorFlow. And you can then see implementations of GANs with TensorFlow. Here I've tried to stay with PyTorch mainly, and that's because I have a certain bias towards TensorFlow and a preference towards PyTorch, but that is more my personal statement. And the book by Babcock et al., they have, you can actually download and go to their GitHub address. So all these modern textbooks, they have GitHub addresses with lots of coding examples. So let's just go back a little bit and lean back a little bit and look at the discussions which we had in connection with the different generative methods, and try to have a kind of bird's view on these type of methods. So in this course, what we started with was what we normally call discriminative methods. And in that, under that category, which has often been the traditional machine learning approach, that means that you fit data to some kind of model, and your model architecture, whatever, can be a neural network, but it can also be a linear regression model. It can be a random forest. And then the idea is that you want to use that one to make predictions. You want to discriminate, as we mentioned in the beginning of the semester, on images or paintings. So you could train a neural network or convolutional neural network on images of paintings of Van Gogh. And then you have a classification problem where true, false, this is a Van Gogh painting, this is not a Van Gogh painting. You train a neural network on that, and then you feed in new paintings. And then your model should be able to make a prediction whether this is a Van Gogh painting or not. That's a very typical example of a discriminative method, because you discriminate between different types of, in this case, paintings or data which you have, and you're able to tell the differences between that class and that class. So with the discriminative methods, since many of you had already coded a neural network, we put more emphasis on convolutional neural networks. Then we discussed recurrent neural networks plus LSTMs, long short-term memory, which is another category of those. These are also called regressive methods, and they have been used extensively in large language models. Then we had the final method, which was autoencoders. So some of these methods can be used as applied to data which are of the supervised type, but you could also use a neural network on data which is not labeled. So you can actually use a neural network to solve a differential equation. And in that specific case, you don't have any labeled data which you use in the solution of a differential equation. A CNN is very much a typical case where you have a supervised training environment where data is well labeled. This is a Van Gogh painting. This is not a Van Gogh painting, etc., etc. RNNs are often used to uncover patterns in time series. Autoencoders can be used as both on both supervised data and unsupervised data. It's actually quite often used in unsupervised data. But these are some of the popular methods which we discussed in the first half of the semester. Then we switched over to the generative methods. And when you look at the generative methods, we're going to make a new image here. So let's just remind ourselves a little bit about some of these methods. We normally split these into methods where we have an explicit model for a probability distribution. And I'm writing PDF, probability distribution function. The typical example which you have encountered is that of a Boltzmann distribution where you have an explicit model. So a typical thing here could be a probability P, which is e to the minus some function divided by some normalization factor. Then you have an explicit probability distribution model. And then you want to train that. So it means that when you do the training, you have to make approximations. And in the approximations, what we have seen are different classes of methods. I'm just going to set up a slot here with approximations. And then I'm going to repeat some of them. So one of the approximations is what we call Boltzmann machines, which we discussed in the very beginning of the generative type of models part. Then we have variational autoencoders. That is another class of models. And then we have the final one, which we discussed last week, which I'm going to quickly remind you of. And that is diffusion models. So these are some of the three main categories, and diffusion models have been extremely popular in imaging. So if you go into software like DAL-E, which is developed by OpenAI, then the typical diffusion models are some of the central models which are used in generation of images. Then we have something here which we haven't dealt with, which is called tractable. And you will then find a typical type of model which are called belief networks. Sorry for the writing here. So the belief networks are normally called Bayesian networks. And that means that your different nodes, etc., are replaced by a probability distribution, which you then will train. These models are often much more difficult to train and are less used. But there's a wide sector of models which you will find in the literature. So tractable means that we always have to look at this balance between flexibility and tractability. So flexibility is something you want to have, so you can adapt the model to new data sets without making too many changes. And Boltzmann machines and variational autoencoders and diffusion models are examples of models which have a lot of flexibility. At the same time, when you say tractable, if you think of a distribution like this P here, which is applied to huge multidimensional models, then the tractability can become pretty complicated in the sense that if you have a 100-dimensional model, you may have a function which is then producing a probability for a 100-dimensional model. And then you would actually need a lot of CPU cycles to just generate one specific event. So when we are looking at these models, there is always a balance we want to strike between tractability and flexibility. So these models here are less flexible when you look at belief networks. They're heavier to train. But on the other hand, you have a very clear explicit expression for the probability distribution. So these are kind of balances which we often have to strike. Then we have another one where we, instead of explicit, we look at an implicit derivation of a PDF. And GANs belong to one of these class. There is a whole other set of methods which we haven't covered, which deal with the Markov chain simulations. Just put Markov chains here. But the more popular methods are those which I'm going to ring in here. So you have GANs, you have diffusion models, variational autoencoders, and Boltzmann machines. So these are some of those which you will encounter most likely when you look at generative methods. So this is in a way to give you a kind of a bird's view on what we have tried to cover during this semester. And today we are going to say a little bit more about the generative adversarial networks. So this balance between tractability and flexibility is actually very important. So let me just quickly remind you of some of these things which we have been trying to do. So what we want at the end is some kind of probability distribution for a variable x. So we have some p theta of x. This is what we want. So that's going to be the probability we want to train. Now, this is normally given in terms of integral or sum over a set of hidden variables. So this can be the variables of a latent space, as we also call them. In a Boltzmann machine, these are normally called hidden variables, etc., etc. And then we would integrate away or sum away these specific degrees of freedom, where we now have a probability which depends on these parameters theta. So these parameters theta are the parameters of the model which we have. If we have a Boltzmann machine, these are the weights and the biases of a neural network, which for the Boltzmann machine. If we have a variational autoencoder, this would be the relation between the data set X and the latent space. I'm going to quickly remind you of that. So what we want then is to draw some data, X tilde, which is as close as possible to the real data which we feed in the training. But then this data is generated by, so this symbol here means that this data is generated by this probability which we are training. And this probability is normally called the marginal probability because we have integrated away other degrees of freedom. So this is called the marginal probability in statistics. And this model p theta is normally then an optimization problem where we have an argmax with respect to the parameters theta. Let me just correct that one. P theta of x. And the tractability then deals obviously with how easy it is to run calculations with the probability we have trained. The flexibility is about how flexible this distribution is. And one of the things which we also use in this case is an extensive use of the product rule from statistics, the conditional probabilities, and Bayes' rule. So one of the things which we also introduced was actually this. So this is the product rule, where we have the probability of having X given H. multiplied with the probability of being in H. So this is called the product rule. And this quantity which we looked at, in particular when we looked at the variational autoencoder, and when we moved to diffusion models last week, diffusion models are nothing but what we might call stacked autoencoders, where we make small perturbations from the latent space to another latent space. And if we think of variational autoencoders, which was one of the models we have spent some time on, then what we would have would be some space, which we call the X space. This is our data set. So we have a data set which we feed in. Now, from that one, we are going to a so-called encoder part, where we now find a relation. So we're actually trying to find a probability of going from X, so given X, what is the probability of H? So this H is going to represent a latent space, which then in principle represents a reduction in dimensionality, so that we just keep track of the essential features. So going back to what we did with the autoencoders and the principal component analysis, this is a reduction in dimensionality. We then encode a probability. So this probability P of H of X is proportional to a model which we make, which depends on some variables phi of H given X. So this Q of phi is the model which we typically make. And in the variational autoencoder, this is normally set to a multivariate Gaussian distribution. So that's a typical model which is used in the training. Then this makes a transition to a latent space. So this is normally called the latent space. And in that specific case, we have the variable H, and we are able then to make a probability distribution which depends on the parameters theta of just H. So in Bayesian statistics, this is called the prior. In that case as well, we make a model for this distribution P of theta or for H, which is typically just given by a normal distribution with a zero mean value and variance equal to 1. So in the training, there are components which you fix. So in making this dimensionality reduction, the idea now is that this space H, which we have here, is smaller or equal than the dimensionality of your input space. So uppercase H here is actually the space where all the small guys live. And the idea is that the latent space is normally much smaller, like we did when we discussed autoencoders. So with that, we can then use Bayes' theorem and the product rule and reconstruct the decoder part. And in the decoder part, what we do then is that we obtain a new probability. And this is the one which is trained now as a Monte Carlo integral by calculating expectation values. And this feeds back to a probability. So this produces the final marginal probability, which is given by an integral over d of h. So we integrate away this other degrees of freedom because we are just interested in a probability as a function of x only. And this is multiplied with p theta of h. And then in here, the final product here, so let's just put an arrow here, is that we produce a new image, for instance, which we call x tilde, which is now generated by this model p theta of x. So you could think of the x which you have here as images of horses, and then you train a probability distribution, which then is going to reproduce new horses x tilde. And hopefully these horses are lookalikes of real horses, but you can also use this probability to generate new horses, pink horses or violet horses or whatever kind of color you like. But you have a model then which should give you a horse and you can decide what kind of color you want. So the idea with these generative methods is that you have a probability distribution, which you then can use to generate new data. Yeah. Yeah. Say it again. So the latent space becomes constant in the sense that you decide what are the distributions for Q. Yeah. Because in the integrals, there are some of the integrals which then become easy to calculate, and you would calculate them analytically. And you do the same thing when we do diffusion models. So diffusion models is actually us changing this probability distribution, which you see here, this transition here to the latent space stepwise. So instead of just making, like here, a big step, you make many small steps. And that means that you're making an image which becomes more and more blurred. And then when you've done that, you reconstruct it step by step again. And by doing this small perturbation, the hope then is that this gives a much more reliable description of a given image which you have. Okay, so this was essentially the kind of setup for the models which we discussed. So let's go back a little bit to the slides from last week and say a little bit about diffusion models before we go over to the last models this semester, which are the popular generative adversarial networks. So if we now go back to last week, I just wanted to quickly remind you of what we did then, is that when we look at these diffusion models, the basic idea is to make small stepwise changes. So instead of us in a variational autoencoders to make just one step here, we split this up in many small steps. Now, all these Q of phi's, which you see here, are given by a Gaussian distribution. So that means that the integrals which follow can all be calculated analytically. So in the process, this is something which we went through. So let me just set up the integrals which we ended up with. So typically these encoder transitions are now given by Gaussians, which are only slightly perturbed from transition t-1 to t+1, or no, t-1 to t. So you make many small steps. So the image gets in a way denoised. And then when you have that one, you can reconstruct. So the final distribution here, which you have at the end after all these transitions, is then given by a normal distribution with zero mean, and like you had in the latent space. So when we're optimizing this, this is now the kind of equation which we ended up last time. So if I scroll down a little bit, we actually went through these discussions. We end up with a calculation of a set of expectation values. Some of these can be calculated analytically, and some of them have to be evaluated by Markov chain Monte Carlo sampling. And the first term, which you have here, is a so-called reconstruction term, and that predicts the log probability of the original data sample given the first latent step. And this would also appear in a standard variational autoencoder and is often trained like you would do with an autoencoder. This term, which you have here, the second term, is also called a prior matching term, because we have a final prior here, which then brings us back to x0, which is the one we want. This is the x tilde you had in the on the whiteboard. And this is nothing but what is called a Kullback-Leibler divergence, where we calculate the expectation value of the ratio of two probabilities. And if these two are close to each other, then this Kullback-Leibler divergence is equal to 0. So this is normally minimized so that when the final latent distribution matches the Gaussian prior, this means that this term often doesn't require an optimization, and it has no trainable parameters. And if you assume that you split this in many, many small steps, then the final distribution is going to be a Gaussian, and this term becomes effectively equal to 0. So where you actually spend most of your cycles is into the last term. And that is called a consistency term. It attempts to make the distribution at xt consistent from both forward and backward processes. And it's called a denoising, because when you add a Gaussian more and more, you make your image noisier and noisier. And the hope then is that when you do this after many time steps, that you actually reach a best possible description of the probability distribution you need. So the diffusion model is, in a way, something you can view as a stacked variational autoencoder. And the thing which is nice is that we know the lower limits of these expectation values. So the lower limit, like the Kullback-Leibler divergence, is 0 if these two probabilities are the same. And that means that you typically end up with a lower bound on what you might expect from the integration. And setting a given probability distribution, if we go back here, by assuming that these are given by Gaussians, it means that many of the integrals can actually be calculated analytically. So whether you have a Gaussian or not depends obviously on the type of problem you have. But a Gaussian is normally the preferred distribution. So both with variational autoencoders and diffusion models, you often assume a model for the latent space, which is given by a Gaussian distribution. So that means you don't have any trainable parameters, but you have a set of hyperparameters, which you then need to change if you want to try new parameters. So if you think of you setting up a neural network, it's pretty similar to that. So your neural network has a given number of hidden nodes, a given number of hidden layers. It has activation functions which you set, and it has some hyperparameters which you set. So you could now say that the activation functions are these Gaussian distributions, and your hyperparameters would then become this mean values, which are putting up here, this alpha of t times, because the mean value is given by the x from the previous one times a parameter. And this is something you would then fix from the beginning of the calculation. And that plays the same role as a hyperparameter. If you think back to when you use ReLU or ELU in a neural network, you had some parameters in the ELU function which are set, and you just keep them fixed throughout the calculation. So clearly, every time you're running these kind of networks, there is a lot of hyperparameters which you could change in order to see if you make a better reproduction. Now, the typical networks which you can set up is something you can actually decide yourself. And if you look into the code which you have here, which is a code which I have taken from an article, and you can find a link here to this article. It should be actually not that. Yeah, the codes which the code which I've taken here is actually a code which trains on the MNIST data set, and I have borrowed extensively from these two references here. And it uses something which is called a UNet. There's a type of convolution neural network architecture that is primarily used for image segmentation tasks. So in this specific problem, what you have is a diffusion models will gradually corrupt the data by adding Gaussian noise over a sequence of time steps. And then the corruption schedule is typically linear or cosine invariance. And during training, the network is optimized to predict the original noise added at each time step using a mean squared error loss. And then you have an inference where you start from random noise, and iterative applies the learned denoising steps to generate new samples. And you can feel free to take a look at this. You will see typically the parameters, the number of diffusion steps which you need to set up. You need to set up, since this is the MNIST data set, you need to set up obviously batch sizes, epochs, the learning rate as before. You need to set up the optimizer you want. The image size, which is now the full MNIST data set, which is a 28 times 28 image. This now takes the data sets and resets it. So this is using, as you can see, it uses PyTorch here. And then there's this simple net, which is actually an example of a convolutional neural network where you actually compress your data to something which is more tractable for the diffusion model. So you can think of the simple UNet here as a way to reduce the dimensionality of your images. So there is a convolution step. So this is something which is done often in connection with these models in order to reduce the whole dimensionality. And then there is a forward diffusion part. which corresponds to the equation which we had there. There's a cost-loss function, and then you have the training loop here. And then there's the reverse part, which again follows the equations here. And then finally, you would then generate images here. So I'm not going to run it because it takes quite some time. And you can see I actually started it before the lecture, and it's still busy here. So it's still running. So many of these models take a lot of time to train. Okay, so what I want to do now is to move over to the discussion of generative adversarial networks. And that will be the last topic we cover this semester here. So let me then just switch. So as I said, it's pretty common in many of these models to actually, if you're dealing with images, to reduce the dimensionality of the image. And then it's pretty normal to run everything through, let's say, a convolutional neural network first. So let me just switch a little bit to the here. Okay, so a generative adversarial network is actually a deep neural network which consists of two networks. And these networks can actually be standard neural networks. So you have one network which is called a discriminative or discriminating network, or just discriminator. And then you have another one which is called a generative network. And the whole idea here is that you, through several iterations of generation and discrimination, the idea is that these networks will train each other while also trying to outsmart each other. So in a simpler version, the two networks could be two standard neural networks with a given number of hidden layers and parameters to train. And the generator we have trained can then be used to produce new images, which then the discriminator is trying to judge whether this is the correct image or not. So typical people could say that the generator is then a kind of fake generator, which then starts with a latent space, which could be a noisy image, and then tries to make an image. And then this is now studied by the discriminator, which then judges whether this is a fake image or not. And then it goes back and forth. And at the end, you would have trained a probability distribution, which allows you to implicitly say what kind of images these are or generate new images. So discriminator is something which I will label with a uppercase letter D. That estimates the probability of a given sample coming from a real data set. It attempts at discriminating the trained data by the generator and is optimized to tell fake samples from the real ones, which is our data set, which we feed in. And then you say that the discriminator tries to distinguish between real data and those generated by the generator. And the generator outputs synthetic samples given a noise variable input. And this is trained to capture real data distributions in order to generate samples that can be as real as possible, or in other words, can trick the discriminator to offer a high probability. At the end of the training, the generator can be used to generate, for example, new images. And in that sense, you have trained a model which can produce new samples. So we implicitly say that we have defined a probability. So the generator is then used. If you want to make new examples, you can then use the generator to do that. So what kind of training is this? So many of these type of models, which are generative ones, are often unsupervised models. You are not limited to generative methods. If you think of a neural network, when I solve a differential equation, you generate a solution. And if that solution is a probability distribution, like you would do in quantum mechanics, your wave function squared is a probability. So if I solve Schrödinger's equation with a neural network, I actually generate a probability. So you can think of a neural network also as a generative method. But generative methods per se, they're really tailored to generate a probability distribution, either explicitly, when you have an explicit model like a Boltzmann machine or variational autoencoder, or implicitly, like you do with a generative adversarial network. So sometimes there is a kind of floating transition between these different categories of machine learning. And as I said, GANs, they are of, yeah. 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 Absolutely. So you actually, in its simplest form, GAN can just be some simple neural networks which you train against each other. And that's the kind of setup which you will see in the lecture note. The program which I took from Rashka's textbook is actually two simple neural networks which are trained against each other. And you will be surprised to see that the neural network, and that's why in the beginning of the semester we put some emphasis on neural networks and CNNs, because they often enter many of the more advanced methods. If you remember back what we discussed about Boltzmann machines, the energy function can be a convolutional neural network. So instead of you having an explicit expression for the Boltzmann machine, as we called it, you could let a neural network or convolutional neural network be the entry to your energy function. So this is something which gives you a lot of flexibility, and that's why it is so important, both when you teach, but also when you work with these things, to have an efficient code for neural networks and CNNs or RNNs, because you can use them to stack them into all these other models. So you can design these architectures which also work in a semi-supervised learning. So it's they are pretty flexible. And there are several examples which I've added here. So you can use both labeled and unlabeled data. And these are often used in three most commonly used contexts, like with labeled data, supervised, with unlabeled data, unsupervised, and then you have it with a mix of all of both. So these two models actually compete against each other during the training process. And the generator, as I said, is trying hard to trick the discriminator. This is just a way of saying things. While the model D, the discriminator, is trying hard not to be cheated. And this interesting zero-sum game between two models motivates both to improve their functionalities. This also leads to some problems with the training and also with the generation of gradients, because we will have to balance two terms. And then we actually have, when we calculate the gradients then with the parameters, we are taking the difference between two gradients. And taking the difference can often lead to problems of numerical stability. We're coming back to that at the end. So these models have been extremely popular. They are very simple to implement. They were actually presented by Goodfellow in 2014. So for those of you who have looked up this textbook by Goodfellow, Benjo, and Coville, it's actually one of these authors who invented this model back in 2014. And according to legend, this was actually something which Goodfellow cooked up just for the fun of it after a pub visit. So pub visits can be helpful. That's just a legend. It may not be true. So here you can see some of the examples of how these methods are being used. So both for image generation, text-to-image analysis, face aging, etc., etc. Now, nowadays, so I would say that historically, these methods, the popularity peaked around 2021, but then lately diffusion models, which we discussed last week and the week before, have in a way taken over. But as you know, this field of machine learning and deep learning is something which moves pretty swiftly. And we don't know what will be the next generation of popular models. So I just wanted to go back a little bit to the whiteboard and say a little bit about the typical training here. And then we go back to the slides and look at some of the mathematics. No, not that one, sorry. I should have this one. So let's just summarize a little bit. So a typical, typical setting for G, the generator, and D, the discriminator, is a neural network. Is a simple multi-layer neural network, can have just one layer, a simple NN. So that means that if you look at the architecture of this generator, you could just feed in some noisy data. So that means you could just set up a Gaussian distribution and generate an image with a Gaussian distribution, or just generate data randomly. And then you would feed that one into a neural network. You can decide how many layers you want to have. And at the end, this is going to produce an image. So suppose now that you are dealing with the MNIST data. So if we now set up the G part, so the architecture of a architecture, yeah. You could think of this as having an input layer where you just give a given dimensionality. And that input layer receives then something like a vector of a given dimension, which could be sampled from a Gaussian distribution, just as an example. So the input layer, you could decide the dimensionality. So we could say now, and this is just an example I'm cooking up. So with, let's say, 100 dimensional, 100 dim vector, which is sampled from a Gaussian distribution. Now, the example which we have in the slides for this week deals with the MNIST data. So what we could do now is to let this pass through different hidden layers. So at the end, we produce a figure which has a dimensionality which corresponds to the MNIST data. And if you remember back the MNIST data, a typical image was something like 28 times 28 pixels. So typically here, this is normally called also the latent space. And this latent space is assumed to be much, much smaller than the final dimensionality you're looking after. So we would often call this for the latent space. And this latent space, which I'm going to call for H here, is normally much, much smaller, or it's actually smaller. So I'm just putting smaller equal to the final space, which we are interested in. So X is the final space, as we used in the diffusion model and also with the operational autoencoders. So you could then think of, if we now keep moving, so we could have different dense layers, which then build up an image which has the right dimensionality. So if you think back to a neural network, you would typically start with an input image. And then for the classification problem, to say whether this was number 0, 1, 2, and so on, in that case, you had 10 classes. So your output would just contain 10 outputs, whether it's number 0, 1, 2, 3, up to 9. So then you run this through different hidden layers, and then you would have a final layer, which we would call just a reshape layer. And since we are doing a MNIST data, it means that you would produce something which has an image, which now is 28 times 28. So this is the flattened vector of an image, which is 28 times 28. And that produces an output, which is now an image of 28 times 28. So the flattened vector is 784. You started with 100 and you gradually build up this image and you run through different layers with a different number of nodes, activation functions, etc. And at the end comes something out. This is most likely in the first run, not 0, 1, 2, 3, etc. Okay? So You can have as many hidden layers with the dimensionalities as you want, but the whole idea is that you're going to use these hidden layers as a way to train and produce an image. So in the last output layer, this is where you have the final image, and that means that the network will generate a batch of images depending on how many images you want to produce at all. So the typical MNIST data has something like 60,000 images with 28 times 28 pixels. So that means that you could run this network to produce 60,000 images over dimensionality 28 times 28, but starting with 100. So this 100, which I put in the beginning here, is just a number I cooked up. You could set this up in terms of powers of 2. So instead of having 100 here, you could make something which goes like 2 to the power of something. Okay? So this is very much up to you. This is the way you would train that one. And after you're done with the reshape layer, then you need to set up D and its architecture. And then after the break, we're going to look at how these are going to compete against each other. So in this specific case, what you're going to do then is to take your images and then you produce an output, which you then want to compare with what the generator is producing. Okay? So it can be as simple as that. It receives an image of a given shape, and then you run through a neural network, and then you flatten it, you reduce the dimensionality, and the last layer could then be, again, a dense layer with a neuron which outputs a single value if you have a single classification, a simple binary case, or more classes. And then you would compare to that what the discriminator is producing. No, sorry, the generator. And the two are going to compete with each other. Okay? Yeah. So, yeah, if it's a binary, it's a yes or no. And what you would have from the generator, when you have produced the image, then you're going to see whether this image is, or it could be yes or no, or it could be 10 classes. And that means it falls into 0, 1, 2, 3, or whatever. So the generator here would produce 10 images, 10 possible images. The discriminator also tells you which one of these it is. And then you have an output from the discriminator, which you compare with the output from the generator. And then the two are going to compete with each other in finding out a balance so that both of them produce the same type of images, the same output. Okay, I'm going to make a small break here. So let's put in some more details to the discriminator. So the typical setting then, if you set up a neural network, is that the initial layer, it would then receive the input. And if you're using the MNIST data set, this would be an input of 28 times 28 pixels. So this means that the initial layer receives the input. And since we are dealing with the MNIST data set, the original data set has 28 times 28 pixels. So that's the shape. And then you have something like 60,000 images. Then you can have a series of hidden layers where you can actually change the dimensionality. So you can reduce it. So instead of having, because this gives you, if you flatten this out, it gives a vector of length 784. And then you can reduce it in the same way as you put up in the generator. So in the generator, we started with something which had a length of 100. And then you can gradually reconstruct it in the generator case. So suppose you start with 100, and then you have the next hidden layer. You can say that then the dimensionality is 500, and then you can move on and make it big and bigger till you have the final output. Here you would go the same way, but opposite. So you would have hidden layers where you can reduce the dimensionality. So you can have several hidden layers, and they reduce the dimensionality. And then the last layer is normally, which is called the output layer. That is, again, a kind of dense, typical dense layer with one unit only, a neuron. And that typically has the sigmoid as an activation function, and it outputs just a single value. And that single value can be either 0 or 1. A value of 0 indicates that the provided image is fake, and a value of 1 indicates that the provided image is correct or real. So let's just put this on. So the last layer is normally a typical dense layer and has one unit. Which is a neuron. And this neuron, actually one of the many typical settings, as I've seen in the literature, has one unit with a sigmoid function. And that outputs either 0 or 1. So if the output is 0, that means that this is a fake image with only 0 or 1 as outputs. And 1, then it's a real image. So let me set up some basic mathematics for how you actually optimize this discriminator and the generator. So let's try to have a look at that. And then I'm going to go back to my slides. Let me bring that one back again. Just a moment. Yeah, exactly. Yeah, exactly. So let me just share the right file. So in the slides here, so this is material which I borrowed from, amongst other Rashka's textbooks. So if you go into chapter 17, you will find many of these details. So you define a probability which is used by the generator, and this is given normally by either uniform distribution or a Gaussian. So if you go back to what we had on the whiteboard, the input could be numbers which are generated, like as I mentioned, by a Gaussian distribution, or it could be a uniform distribution. So this is what we call the latent space, and that space, which then defines these variables h, is normally much smaller than the original space. As I said, as an example, you could have something which just contains a vector of length for 100, whereas your MNIST image has a vector of length 784, since you have 28 times 28 pixels. So this h is again something you can play around with when you're setting up the network. And it's pretty common to either have a uniform distribution or a Gaussian distribution. Then we define the distribution of the generator, which we want to train as P of G. And that's a generator's distribution over the data X. And then there is also distribution here over the real sample. So that's your original input. Okay, so these are just definitions here. Then the simplest formulation of the model is, and this is what actually Goodfellow formulated, is a game theoretic approach, a zero-sum game, where you pit two neural networks against one another. So you define two neural networks, one generator and one discriminator, and the generator directly produces samples. So this Z here could be your latence variable. And the discriminator attempts to distinguish between the samples which are drawn from the training data and samples drawn from the generator. So it tries to tell the difference between the fake data produced by G and the actual data samples we want to do predictions on. And the discriminator outputs a probability given by X, and then you have this theta, where this theta are just the different variables of the network. So the thetas here are actually the parameters of the network, which are optimizing with respect to. So the simplest way to formulate this is actually you have a function which determines the reward for the discriminator, while the generator gets the conjugate reward. So if we now look at the way you would optimize this, is that the procession, now let me just bring back this text here. So during learning, both of the networks maximize their own reward function so that the generator gets better and better at tricking the discriminator, while the discriminator gets better and better at telling the difference. And what you do then is that the kind of, if the generator ends up succeeding perfectly, then the discriminator will do no better than just a random guessing. The progression in the training is something which then means that the discriminator feedback gets less meaningful over time. If you continue training after this point, then the generator is effectively training on junk data, which can undo the learning up to that point. So you would typically stop the training when the discriminator starts outputting just 50%, which is just as tossing a coin. So the typical way this training is done is that you have a expectation value, which is calculated on the log of the distribution from the discriminator, and 1 minus the log, minus D, which is then supposed to be the data which is rejecting what you're actually looking at. So one of the ways to look at this, it seems I have been repeating things here. Oh, sorry, I didn't see that one. I have some slides I have duplicated here. Oh, I didn't see that before now. Sorry, this is a copy and paste. Okay, so you want to have make sure that the discriminators over real data are accurate by maximizing this probability. So remember now that this P of R, if we just go back a little bit, we define this P of R to be the distribution over the real sample. So if we just go back again here, and then when you're given a fake sample, which has this probability here, the discriminator is expected to output a probability D based on the discriminator close to 0 by maximizing this quantity here. The generator is trained to increase the chances of D producing a high probability for a fake sample, thus to minimize this quantity. So when you're putting these together, what you're doing then is to set up what is called a min-max game, where L stands for the loss function, where you plug in what the generator and the discriminator are producing. And that means that we are setting up two expectation values, where we generate these X's according to the real data, and these H's according to the latent data, which then could be a Gaussian, or it could be a uniform distribution. And these two quantities then, so this would actually then be replaced by what you do with the generator. And then this first quantity has actually no impact on G during a gradient descent update. So these probabilities, now these expectation values, which you see here, they are obviously optimized. The optimization runs through you calculating the gradients of these distributions, these expectation values. So if you look at the loss function then, which is in principle an integral over these two quantities, so you have the P of R for the real data and the one which is made from the generator, then you're trying to find a balance between these two quantities. And what you can do then is actually since you're only interested in what is the best value of d of x to maximize this one, what we can do then is just to look at the quantity which you have inside here, because this equation here is valid for all x's. If you do that, I'm just introducing some additional variables here. So we have x tilde, which then replaces d of x here. And then I simply put an a equal to p of x and b equal to p of g. If you do that, this function just becomes like that. And now I want to find the derivative, because then what is inside the integral, so we can safely leave that one out, because we want to see what maximizes or minimizes and maximizes. So we are taking the derivative of this quantity here with respect to this x, and that gives us simply now, because x is the d of x, then I'm getting this relation here. If I use this relation by just setting up the derivatives and I require this to 0, then we get the best value of the discriminator, which is now given by a. And just let me remind you of a here. So a is this probability, and b is the probability from the generator. And that gives us a quantity here, and we know that this one has to be between 0 and 1, because the probability takes maximum values of 0, or no, minimum value of 0 and 1. And once a generator is trained to its optimal value, then the two probabilities are getting close to each other. And when these are very close to each other, then we see that this becomes equal to a half. And if you look at the codes which you have in the lecture notes for this week, this is actually what you will get when the training is getting close to an end. So this is a kind of training limit. So when both G and D are at their optimal values, we have these two probabilities being close to each other. And this D asterisk, which is now the optimized value, is equal to a half. That means that your loss function, when you plug everything in, is just simply you plugging in these values, and you can show that that is equal to -2 times log 2. That's your loss function. Yeah, I'm going to skip some of these things here, and you can look them up here. So there are some problems with GANs. They are pretty popular, but it's actually hard to reach equilibrium. So they are trained simultaneously to an equilibrium, to a two-player non-cooperative game. However, each model is updating its cost independently with no respect to another player in the game. And so updating the gradient of both models cannot guarantee a convergence. So that's a problem with GANs. There is also the problem of vanishing gradients, which we also encounter in many other implementations of machine learning methods. So when the discriminator is perfect, then we are guaranteed that this d of x is equal to 1. That is a perfect one. And this d of x is 0 when x is just an element of p of g. So what happens then is that the loss function falls to 0, and we end up with no gradient to update and the loss during learning iterations. And then you can encounter situations where the discriminator gets better and the gradient vanishes fast. So there are some problems with GANs. So one is that the discriminator behaves badly and the generator does not have accurate feedback. And it does a great job, and the gradient of the loss function drops down close to 0, and the learning can become slow. So these are some of the problems. There are lots of improvements. Typically, the calculations, when you're comparing the two probabilities, so I'm going back a little bit, in the lectures on diffusion models and the variational autoencoders, we introduced what's called the Kullback-Leibler divergence. So let me switch back quickly to the whiteboard and remind you of that. So just as a quick reminder, one of the measures for the probabilities which is used in these trainings is what is called the Kullback-Leibler divergence. And we encountered this when we discussed in detail the diffusion models and the variational autoencoders. And this is a measure of two probabilities and how far they are from each other. So the DKL divergence of P of a probability P with respect to a probability Q is then given as an integral if we have continuous probability of a domain D of P of X of log of P of X of Q of X dx. And you see then that this DKL of P and Q is actually equal to 0 if P of X is equal to Q of X. So this is used as a measure for the distance between two probabilities. And when we set up the equation for variational autoencoders, we actually use this relation here to evaluate the integrals. And we know that this has a lower limit, which is equal to 0. And that is something which we used in the training of the model. This Kullback-Leibler divergence, if you look at it as well, this is something which we could write as the expectation value, where we extract X according to P of X. And then we have the expectation value of log P of X of Q of X. So when we did the variational autoencoders, we actually didn't need to evaluate this one because we had a model for this in terms of a Gaussian. And then we had an analytical result for it. When we do the diffusion model, we were also assuming that these Qs were given by Gaussians. So the Kullback-Leibler divergence is one of these possible measures, but this is not used normally because it is not symmetric with respect to P and Q. So a more common measure, which is also used in the field of GANs, is something which is called and this is not a relative of mine, it's called the Jensen-Shannon divergence. So this is another measure of the similarity between two distributions or two probability distributions. It is based on this Kullback-Leibler divergence, but however, it is symmetric in the probabilities and can be used to measure the distance between two probability distributions. So this, so we are going to use JS. So this J of S of P and Q, and this is the quantity which is often used in GANs, but you also have improvements to that, which we are coming back to. But that's given by the Kullback-Leibler divergence of P and P plus Q divided by 2 plus 1/2 of the Kullback-Leibler divergence of Q. And you see that this is now symmetric with respect to P and Q. If you take the Kullback-Leibler divergence as it stands, it's not symmetric. So because the Kullback-Leibler of DKL of P and Q is actually given by P of X, but let me just restate it, divided by Q of X of D of X. And you see this is not symmetric under the interchange of P and Q. And this is one of the reasons why this Jensen-Shannon divergence, as it's called, it's also called the information radius. So there are many names of total divergence to the average. This is one of the reasons why this is often used as a kind of measure of the quality of the two probabilities. So if you then go back to the, just go back to this one, to the slides. So the function which is often used then is actually this, as I said, this Jensen-Shannon divergence between these probabilities, POR and POG, the one from the real data and the one from the generator. And when you compute that one, you can actually show that this becomes equal to the quantity which you see here, where you have a log 4 plus the cost function with the optimal probability here. And that means that the loss function or cost function is actually given by 2 times this divergence minus 2 times log 2. So essentially the loss function of a GAN quantifies the similarity between the generative data distribution and the real sample distribution by this JS divergence when the discriminator has reached its optimal value. The best G that replicates the real data leads to the minimum minus 2 log 2, which is aligned with these equations above here. So you have remember that you have a min-max problem here. So you want to have a distribution where you have a minimum for the generator and a maximum for D. So these are some of the more mathematical considerations which you will encounter typically when you look at the GANs. And however, there are actually other measures which have been introduced, and one is called the Wasserstein distance, which I will not discuss here, but you will find the introduction to that in Rashka's textbook. So as I said, this last lecture is more meant to give you a kind of bird's view on GANs. And then if you want to implement them, you have code examples, both in the lecture notes here and also in different textbooks. So the code which I put into the lecture is actually given. It's exactly the same code which you will find in Rashka's textbook. So I'm going to just say stop that one. Okay, so if we go back to the Jupyter Notebook, and if you scroll down here, you will then find basically the same thing which you had in the in the slides, and this is a generator network, which again is applied to the MNIST data. And as you can see here, this is a generate network. I start with 100 as the length of my vector, as I discussed. And I have just one hidden layer. And then I have the output layer, which has the same dimensionality as the image, 28 times 28. And then I'm setting up the hidden layer. So this is actually the generator. And in my case, I'm using the tan-H as an activation function in here, and also have the leaky Relo here. And then I have the discriminator network, which takes in the input, but then it has the hidden one, so it just has one hidden layer. And this hidden one has the same dimensionality as the one, the other generator. Is that a prerequisite? Like for so it's normal that this is done actually. Yeah, that's as far as I understood it actually. As I said, I mean, I haven't done research on GANs. So what I'm doing now is simply that I am entering a little bit more shaky grounds, and I'm simply repeating what's in the textbook by other people. So my cup of tea is more into generative methods like Boltzmann machines and variational autoencoders. So, but you see now the thing is that you can decide yourself, I mean, how you want to set up this generator network and the discriminator network, whether you want to have a neural network, a convolutional one, you can have an RNN, etc., etc. And then you have the, so this just sets up the model, and then you define the training set, and the training set is the MNIST data, and then you have then the data from the generator where you just create noise. So you can decide, as you can see here, the common choices, as I mentioned, are either uniform or normal. And Z is the size of this latent space. And then you define the batch sizes, load the data, and then here you have a uniform distribution, and then you train the GANs, and this just continues. Actually, this will also take some time to run, so I'm not going to run it in the lecture here. But feel free to take a look at these codes and try them out. So how many of you have already, I had a feeling that at least 2 groups here have already implemented GANs, right? With quite some success. Yeah, roughly. So keep in mind now for the project, we are not expecting that you will get perfect results, because the course is, after all, 10 credits. So that means the whole idea is to explore the different methods and that you have an understanding of what the methods mean, so that you can write a qualified assessment of what the methods are. But we don't expect that you will have time to refine these models, because typically here people would play with different hyperparameters, different depths of the networks, etc., etc. So the most important thing for this course is that you have an understanding of what enters, and then we are fully aware that there is a time limit and that not everybody has access to you should keep in mind that we do have access to machine learning nodes at the University of Oslo, and that will allow you to run larger models. But we don't expect you to have a fancy, perfect training of complex models. So this would be more the topic of a more dedicated thesis project, where you have typically half a year or 1 year at your disposal. So if you don't get a perfect training, don't be disappointed. The important thing is that you have an understanding of what is being done. That's the most important thing. And that you're able to describe it and you can point to further improvements. Okay, I'm going to stop here.